Alrighty, this is section 6.2, and this is another recurrence example. And so we're solving x of n plus 1 equals axn plus some b vector. And so it's an affine relationship, recurrence relationship here. And so, you know, they pretty much go through, I'll call it 6 steps, I guess. They, you know, derive general solution, or I'll go with generic solution. And so by induction, just building up from x0, we know that our final xn could be written instead of this recurrence relationship. We could write it as our matrix a to the n x0 plus the sum I equals 0 to n minus 1 of a to the I, all that, and then times our b vector. So since we're given x0 to start with and b, you just have to compute these other two things, these powers of a and the sum of them in the one case. And well, that could be extremely computationally intensive if the matrix A is not diagonalizable, which it may not be. But if it is, makes our life much easier. So our second step then is to kind of see, you know, is it diagonalizable? We get our eigenvalues and eigenvectors. Of A, and from that then, so we'll get some, you know, lambda 1 and a corresponding x1, we better call it e1 because we've got a bunch of x sub stuff going around here. So we'll call it e1, and we'll get a lambda 2 and an e2 if this is a, you know, two-dimensional system, which we'll stick with that. So we'll get those. Then 3, we create our diagonal matrix D equal lambda 1, 0, 0, lambda 2, and P, and we make that from our E1 and E2 columns. And then we'll also have to compute P inverse. So we'll need that. Okay, so once we have that, then we can write a to the n is P d to the n, P inverse. But what they do, they don't really do much, you know, point this out very well, I don't think, but generally speaking, and they hide a little bit in their first example as to what they did because they have that eigenvalue of exactly 1, which ends up being a slight problem. But we can end up writing this as, actually, I should, generally speaking, now if neither of the lambdas is 1, we can very nicely, well, I guess even if it is 1, we can end up writing it this way. Yeah, I guess we could write it, even when it is 1, we can write it this way. But lambda 1 times some matrix U plus lambda 2, to the n, lambda 1 to the n, lambda 2 to the n, times some matrix V. And they kind of hide that in what they do, but that's actually what they've done, is they've found that, but they ended up factoring a 1/2 out of their U and V in their example, and so it doesn't, you don't notice that they have their eigenvalues out in front, but that's what they do, and so that is very nice. And then step 5, so we get a to the n, and we get it in this nice form, so that then if we so then we need to use this factorization idea that a to the n minus I is equal to oh, and actually I should point out that the U plus V here, when you do this, is equal to the identity. So that's very nice as well, and that's part of what helps us in this step 5. Okay, so a to the n minus I times that summation that we want, I equals 0 to n minus 1 of a to the I, so it factors as that, and times a minus I. Okay, and so they point out that you can do that, and so you could use an inverse. Actually, I think the inverse is probably harder to use, but they point this out, and so I'll point it out. So you've got a choice here. You can either then use this relationship and an inverse of that thing, a minus I, to get that the sum I equals 0 to n minus 1 of a to the I is equal to a to the n minus I times a minus I inverse. So that's one way you can do it, as long as that inverse exists. And they did not do it that way because the inverse didn't exist. They did it this way. And like I say, I think this is just easier, actually. So a to the I. So if any given a to the n is made this way, lambda I to the n, or lambda 1 to the n times u plus lambda 2 to the n times some constant vector v, well then actually, you know, we can sum this up. I equals 0 to n minus 1 of lambda 1 to the I times u, and plus lambda 2 to the I times v. Now, I equals 0, notice you get 1 and 1, so you get u plus v. Well, the idea is that, right, a to the 0 is the identity, so we really do need this thing here where u plus v equals I. But it does, and so we can write it that way, but that means this is I equals 0 to n minus 1 of lambda 1 to the I, all times u, plus the sum I equals 0 to n minus 1 of lambda 2 to the I, all times v. So that would be kind of hard, except we know how to add up a geometric series like this, and we know this is 1 minus lambda 1 to the n over 1 minus lambda 1, and that's all times u, plus 1 minus lambda 2 to the n over 1 minus lambda 2. Well, so if I know the eigenvalues and I've already calculated u and v, I just think b here is the easier way to go, just like they did. So, I wouldn't worry about trying to do it that way. And then you see, once we have that, so 6, we can substitute into, results into step 1 up there. And we have x sub n is equal to lambda 1 to the n, u times x0, plus lambda 2 to the n, v times x0. And then plus our 1 minus lambda 1 to the n over 1 minus lambda 1, all times u, and then times our b vector, and finally plus 1 minus lambda 2 to the n over 1 minus lambda 2 times v times our b vector. And there's our solution. Okay, so let's try that with an example. We'll use the same matrix we used for the differential equation. So we have xn plus 1 is equal to 2xn plus 3yn plus 2, and x0 equals 4, and yn plus 1 is equal to 2xn plus yn minus 3, and y0 equals 1. So x0 is 4, y0 is 1, and so we just we start with our really step 2. We know what the solution will look like, so I'm going on to step 2. And the reason I did this is we know the eigenvalues and eigenvectors of this thing. So we have our A is equal to 2, 3, 2, 1 here. And we know that lambda 1 is equal to, what the heck is lambda 1 equal to? Now I lost it here somewhere. Negative 1, yeah. So negative 1, and E1 is equal to the vector 1, negative 1, and lambda 2 is equal to 4, and E2 I chose to write as the vector 3, 2 to keep integers. So you can always do that. This will work just fine. Okay, so there are our eigenvalues and eigenvectors. And so that means our D matrix is negative 1, 0, 0, 4. And our P matrix is 1, negative 1, 3, 2. Now for that P matrix, P inverse was equal to, what the heck was P inverse equal to? 2/5 minus 3/5, 1/5, and 1/5. Okay, so there I have my D, P, and P inverse. So now I go on to step 4. And so a to the n is equal to p d to the n p inverse, which is equal to I believe, according to Sage, I think I need more room, so I'll put it here. So when you get this, you get 2/5 lambda 1 to the n plus 3/5 lambda 2 to the n negative 2/5 lambda 1 to the n plus 2/5 lambda 2 to the n, and then negative 3/5 lambda 1 to the n plus 3/5 lambda 2 to the n, and finally 3/5 lambda 1 to the n and plus 2/5 lambda 2 to the n. So that, notice, I've got all this stuff times lambda 1, I've got all this stuff times lambda 2, so I can just write this as lambda 1 to the n, and my U matrix is the 2/5, negative 2/5, negative 3/5, and 3/5. So there's my U matrix plus lambda 2 to the n, and I'll switch out the lambdas here in a minute, but I wanted to make sure you could see that that's what we had there were the lambdas. And so this is 3/5, 3/5, 2/5, and 2/5. And notice, adding these things up, we do indeed have U plus V is the identity. So that's just a little note in there. And so we have negative 1 to the n, 2/5, negative 2/5, negative 3/5, 3/5, plus 4 to the n, 3/5, 2/5, 3/5, and 2/5. Okay, so there I have my general a to the n, and so I'm ready for step 5, where I'm trying to get that sum I equals 0 to n minus 1 of a to the I. And again, if I use the just the actual summation step, then what I know is this is 1 minus negative 1 to the n, so my lambda up there, and then 1 minus negative 1, and that's all times my U vector, so 2/5, negative 3/5, negative 2/5, 3/5, and plus 1 minus 4 to the n over 1 minus 4. And I've got my 3/5, 3/5, 2/5, 2/5. Okay, and so there I have those. And so now I am ready to simply substitute stuff in again, because x sub n was a to the n x0 plus my sum there, I equals 0 to n minus 1 of the ai, and then times b. Okay, so I have -1 to the n. And what do we have there? 2/5. So I'm going to do the u's and v's here, right? So what are we at? 2/5, -3/5, -2/5, 3/5. So I have that, and then times x0. Oh, x0, what the heck were you? 4 and 1. So this is times 4, 1. And then, I should put an equals there. Okay, then plus 4 to the n. Oh yeah, 4 to the n. I lost where I was here. Easy to do. 3/5, 3/5, 2/5, 2/5 times 4, 1. Okay, so I've gotten the an x0, and so now plus, and I have that summation and each times b, and so I have the 1 minus a -1 to the n over 2, 1 minus -1, and yeah, I need my 2/5, -2/5, -3/5, 3/5, and b, what the heck was that? That was, whoops, where am I? Yeah, okay. Sorry, I hate to make you dizzy that way. Can't find my problem. Oh, there it is. Okay, 2 and -3. 2, -3. And then plus, and here I have 1 minus. Now I can make that 4 to the n minus 1 over 3. So that's what I'll do. 4 to the n minus 1 over 3. And then times my 3/5, 3/5, 2/5, 2/5, and 2, -3. And so there is my answer. Now I can simplify that a bit more. I just need to do those matrix multiplications. I have not done that yet, so I'm going to, well, at the risk of screwing them up, we have -1 to the n, and we get 8/5 minus 3/5 is 5/5. Okay, so I believe we get 1 there. And -8/5 minus, or -8/5 plus 3/5 is a -1. That's interesting. I'll have to think about that. Plus 4 to the n. And we get 12 plus 3 is 15. Yeah, see, we're going to get the eigenvectors here. I didn't realize that. So 8 and 2 is 10/5. So that may be always true. I don't know. I'll have to look, I'll have to look at that. That is, I don't do a lot of solving of recurrence relationships like this, and so it could be I should have known this, right? That's a lot of aggravating calculation we could have saved there by just getting that. Okay, and then plus r1 minus -1 to the n over 2. And here we have 4, and that's a minus, so 4 and plus 9 is 13. So this is 13/5. And -2, -4 and -9 is -13/5. So that's interesting. Notice that's also an eigenvector because it's of the right form, 1 and -1. But notice it's not the right multiple. And even if I brought the 2 in and so forth, it's not the right multiple. And so I'm not sure what's going on there, but again, probably somebody who does this a lot would be able to tell us. 4n minus 1 over 3. And let's see, so times, and let's see if we get a ratio of 3 to 2 on this. We get 6, and minus 9 is a -3 over 5. And 4 and a -6 is a -2 over 5. So yeah, once again we get, that is an eigenvector, just not the one we started with, and that's interesting. So we could simplify this some more. I don't think I'm going to, by taking the 13/5 out of this vector, taking the taking -1/5 out of this vector, and then adding that thing to that thing. Well, why not? Probably doesn't hurt here. So I'm going to take 13/5 out of this vector, and so what I'll get is a -1 to the n, and I'll get a plus 13/10, and then a minus 13/10, -1 to the n, all times the vector 1, -1. And then plus, I'll have my 4 to the n, then here I'm taking a -1/5 out, so that is minus 4 to the n over 15, and then again taking a -1/5 out, that makes that a plus 1/15, all times the vector 3, 2. And so one little bit more here. So I have 1 and minus 13, so I have 13 minus 3 times -1 to the n, all over 10 times the vector 1, -1. And this is plus, I have 15 15ths minus 1/15, so that's 14 15ths. 14 times 4 to the n plus 1 over 15. Whoops, not sure what just happened. Now let me try to get rid of all that. There we go. And times 3 over 2. So, interesting. Okay. So we got it in terms of our eigenvectors, which is not surprising in the sense that like in differential equations, we see eigenvectors have a lot to do with the solution, and so I'd have to look at this a little more myself to see if we could find an even better streamlined method to get our answers. Um, but this worked okay. There's a lot of computation in it. Still, we get an answer. Okay, and I even got that answer in terms of the eigenvectors of my A matrix, so that was pretty nifty. Okay, and we will call that done.